Okay, so for today we are going to talk about constant rate of change and proportionality. Our learning target for today is that you can identify if a function is linear or proportional from tables and from graphs. Okay, so the first thing that you need to have an understanding of is how to read tables and how to read graphs. So typically speaking, if we're talking about a table that's set up in a format, a vertical table typically has your x values on the left side and your y values on the right side. We call that a vertical table. If it is a horizontal table, most of the time our x value is on the top and our y value is on the bottom. Okay, now there are some cases in which that will be inverted, but these are general cases, okay, for the most part. Okay, they do sometimes have cases where it's reversed, mainly with this one. Sometimes they might put the y on top and the x on the bottom, but generally speaking, if it's a vertical table, x is always on the left, y is always on the right. And then when you're reading a graph, it's just like you're reading a book. Okay, so if you read a graph, you read the graph from left to right. Okay, when we read graphs from the left to the right. So sometimes it might start at the top left, sometimes it might start at the bottom left. The position that it starts in will determine the type of slope, which we'll learn about slope later, but it will determine the types of slope that there are, and there are 4 types of slope. But you always start from the left side of your graph and work your way to the right as you're reading your graph. Okay, so now the idea for linear. So talking about these linear relationships. When you think of the word linear, you should see the word line in there, and it should make you think of lines, and lines are supposed to be straight. So when we talk about linear relationships, we are talking about relationships that when we plot them on a graph, then that graph is going to be a straight line. Hey, those of you who have your computers opened up, go ahead and close those. You don't need them opened right now. Don't need the distraction. Okay, when we talk about a constant rate of change, so a constant rate of change, for now on, I'm going to go ahead and call that CRC. It makes it a lot easier for us. And this is also known as the slope. So AKA, this is your slope. Constant rate of change is also called your slope for a piece of a graph or from a table. So for our constant rate of change, we're always talking about the change in our y that's going to occur. It's a constant change in the y that's going to occur over the constant change of your x. So change of y over the change of x. Now, some things that you might want to keep in mind when we talk about x's and y's, there are specific types of values that will always be labeled an x value or will always be labeled a y value. So time, when we talk about hours, seconds, weeks, years, days, okay, that is always going to be x values. So whenever they're giving you a problem in which they're discussing the measurement of time, that time measurement is your x value. When they're giving you topics of money, that's always going to be your y values. And then distance that you travel, that could go interchangeably. Sometimes it could be x, sometimes it could be y. Most of the time it's y, but it could also be x sometimes. Okay? And we'll say distance, mostly y. But there are times in which it will be an x. Okay? So let's take a look at a few examples. You have to have an understanding of how to do this from tables and how to do this information from a graph to be able to identify if it's linear or nonlinear. So for a table, again, you're trying to find the change that's occurring for your y over the change that's occurring for your x. So the left side, like I said, is typically going to be your x values. The right side is typically going to be your y values. And you're wanting to look for your change that's occurring. So off to the side, we're going to put down what the change of x is. So here, we're going from 1 hour to 2 hours. Then we're going from 2 hours to 3 hours. And then from 3 hours to 4 hours. So it happens to be that each time we happen to be increasing by 1 hour. Okay, then for our change of the y, we're going from $10 to $18, $18 to $26, and then $26 to $34. So here we are increasing consistently by the value of 8. So that means our constant rate of change in this case is going to be a positive 8 over a positive 1. Okay, I'm even going to write the positive signs just so that we know, because if there happens to be a negative sign, you need to make sure that you're putting your negatives. So it's a positive 8 over a positive 1. If we were to relate this back to our table of information, that would represent $8 per hour that we're being charged. $8 per hour is our constant rate of change. And since we do have a constant rate of change, then that means that this is a linear relationship. In order for you to be linear, you must have a constant rate of change, because a constant rate of change shows a graph that is a straight lined graph. Okay, let's take a look at problem B. For problem B, this is a graph, and again, for the graphs, we start at the left and we work our way to the right. So we happen to have a few points here. Here's one of the points, here's a second point, here's a third point that they happen to have graphed. So the change of your y's, just so you know, your y-axis is located right here. It's the vertical axis. Your x-axis is your horizontal axis. So when you're looking for your change that's occurring, you're trying to identify from one point to the next, how far up and down are you going, over how far left and right are you going. Okay, so for here, we happen to be decreasing. Now, are we going to count the boxes? Is this value a change of 2? No, because if you look off to the side, this is going from 80 down to what? 60. So this is not going to be changing by 2. This is a change of 20, and it happens to be a decrease of 20. So we're going to put a negative 20 there. Then for our change of our, oh, my pink is gone. For the change of our x, we are going to the right. To the right would be a positive value. Now again, we want to look down here and see we're going from 8 to 16. So what is that a change of? Plus 8, right? We're adding 8. And we're going to consistently be doing this each time. We're decreasing by 20, and then we're adding 8. And then we are decreasing probably by 20 again, and then adding 8. It's just going to keep going on and on. So that means our constant rate of change is going to be a negative 20 for the change of our y over a positive 8 for the change of our x. So when that gets simplified, that simplifies to a negative 5 over 2. Okay, this means that you are going to decrease 5 minutes for every 2 volunteers. This is a decrease of 5 minutes for every 2 volunteers. And is this linear or nonlinear then? Linear, because we have a constant rate of change. So this is considered to be a linear function. Okay, so I'm going to have you guys do problem C on your own. I'm also going to create 2 other problems down here for you to try. So we're going to have this be problem D. Problem D's got the values for X and Y as well. Okay, go ahead and do C, D, and E on your own, please. Okay, let's go ahead and go over problem C. Is this linear or nonlinear? Nonlinear, right? You don't have a constant rate of change when we're taking a look at it. For problem C, we've got X on the left side, where our change happens to be increasing by 5, and then increasing by 5, and then increasing by 5. So we do have consistency here for our change. And then for our change of our y's, we're decreasing by 5, but then we're decreasing by 4, and then decreasing by 4. So we're not consistent. So when we have a change of -5 over +5, this is not going to be equal to a change of -4 over +5. Okay, those are not the same. It's not consistent throughout. It's okay for there to be different changes within your y, but then that means there must be different changes within your x, and it must be proportional. They must make sure that they are equivalent changes. So this is considered to not be linear. So it's non-linear. There is no constant rate of change. It is a non-linear function. All right, for problem D. Problem D, is that linear or non-linear? Linear. It is linear. Your change, here we happen to be increasing by 2, and then we're increasing by 1, and then we're increasing by 3. So automatically people think, oh, that's going to not be linear. However, if you take a look at your y increases by 6, then it increases by 3, then it increases by 9. So if you were to go ahead and set all of these ratios up, they would all be equal to each other. You have a 6 over 2, you have a 3 over 1, and you have a 9 over 3. All of those are going to simplify to the exact same value of a constant rate of 3 over 1. Okay, so that means that it is a linear relationship. What about problem E, linear or nonlinear? Linear. It's linear. Again, same idea. We are now going to be decreasing here by 8, and then we are going to decrease by 5, and then we're going to decrease by 3. For the y's, we are also going to have an inconsistent change. We're going from 47 to 23. That's a decrease of 24. Then from 23 to 8 is a decrease of 15. And then 8 to -1 is a decrease of 9. So again, if we set all these up, we've got -24, -15, -9, and we're going to put them all over their respective changes for x. So -24 over -8, -15 over -5, -9 over -3. Every single one of those is going to be equivalent to each other. They're all equal. You're going to have a constant rate of change that comes out to a positive 3 over 1, or just 3. So that is a linear relationship. It's okay for there not to be consistency as long as they are equivalently not consistent. Cole, second time, head up. Thank you. All right, so let's talk about proportional linear relationships. So we know linear relationships have to be a straight line. They have to be straight because they have a constant rate of change. If we are talking about a proportional linear relationship, not only does it have to be a straight line, but it also has to pass through the origin. What's the origin? 0, 0. Okay, so it must be a straight line and it must pass through the origin. Okay, and the origin again is 0, 0. Okay, so when we're talking about the origin, we mean 0, 0. So when we are graphing this, it's going to be a straight line and it's going to go through that corner part, that 0, 0 value. Okay, if it's on a table, then your table must be able to work its way to the value of 0, 0. Okay, so taking a look here, we have the measurement of speed and the measurement of time. Remember, time is always going to be our x, no matter what. Sometimes a measurement of distance traveled, that can be considered a y value. So I told you sometimes they're going to have these tables flip-flopped. But we do know that time is always going to be our x value. Okay, we do happen to start at 0, 0. So when I'm graphing this part, I know that it's going to be at 0, 0 here where 0 is located. If I'm putting my measurement of time down here at the bottom, since I know that my measurement of time goes all the way up to the value of 5, then I have quite a bit of wiggle room for graphing. So I'm going to go ahead and just go every other value is going to be counting by 1. So skip a line, go to 1. Skip a line, plot a 2. Skip a line, plot 3. Skip a line, plot 4, and so on and so forth until you get all the way to the end and you should have 7. And this is a measurement of seconds. Okay, our y happens to be the speed. So when we're labeling that, we're going to label it the speed that we're traveling, which is meters per second. And I know that I'm going to be going all the way up to the value of 49. So in a situation like this, I need to make sure that when I'm graphing past the value of 49. So I'm going to go ahead and count every one of these lines by 4. So I have 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, and then 56 is what we're going to count up to. Okay, and then I can go ahead and I can plot each of these. I can graph each of these points. At 1 second, I'm at 1 second, I'm at 9.8, which is just going to be a little bit above the 8 value. At 2 seconds, I'm at 19.6, which is almost at the 20 mark. At 3 seconds, I'm at 29.4, so just a little bit above the 28. At 4 seconds, I'm at 39.2, which is almost at the 40 mark. And at 5 seconds, we're at 49, which is just a little bit above the 48. Okay, now because my graph isn't perfect, I can't tell from the graph whether it's going to be linear or not, but I can go ahead and use the idea of linear relationships with a constant rate of change. So we know that the change of y in this case is increasing by 9.8 every single time. Okay, we also know that the change of my x is increasing every single time by 1. So we do have a constant rate of change. Our constant rate of change is going to be 9.8 over 1. So it does make it linear, which is what we're wanting. It needs to be linear. It does pass through the origin. So that means that this is a proportional relationship. This is going to be considered a proportional relationship. All right, on the next page, on the back of your sheet, I want you guys to go ahead and identify the constant rate of change from the table given to you. I want you to plot the table, and then I want you to identify if it's a proportional relationship or a non-proportional relationship. Okay, so for this first problem, we have hours of study and the test score that was received. Who can raise their hand and tell me what is the constant rate of change for this relationship? Jamez? Close, reverse it. It's 16 over 1. 16, remember time is always going to be your x. So that means the other value is going to be your y. So this is going to be your x value. This is going to be your y values. Okay, if we are going to have a 1 over 16 that's occurring here. So we do see that 16 over 1. We do see that we're increasing by 1 every single time that we change our hours, and that our test score in this case is increasing by 16 every single time that we're graphing. Okay, so we do know that we have a constant rate of change of 16 over 1. Remember, it's the change of the y over the change of your x. Okay, so that's going to be 16, so that means that it is going to be a linear relationship. Okay, so is it proportional? Yes or no? No. Okay, so if we were to work backwards, so instead of increasing by 1, we would decrease by 1. To go backwards to take us to a 0. But then that means we would have to decrease here by 16, and that would take us to 36. 0, 36 is not the origin. This is not the origin. So the first point that we would be plotting would be at 0, 36. So it's linear, but it's not proportional. It does not cross through the origin. Okay, if we were to go ahead and graph this, again, the corner is going to be our 0. I would just skip every other line and make those my hours. And since I have to get all the way up to 100, or at least, past the 100, I'm just going to go ahead and count each one of these by 8. You might have done something different, but I went ahead and counted everything by 8, especially since I knew I was having values of divisible by 16. Okay, so we have 48, then we have our 56, we have our 64, 72, 80, 88, 96, 104, and 112. Okay, so it gets me well up past my 100 mark that I would need. And then if I'm graphing that, at 0, I would be up at 36, which is going to be halfway in between. Okay, then I'm going to be at 1 hour and I'm at 52, which is halfway between 48 and 56. At 2 hours, I'm at 68. That's halfway between 64 and 72. At 3 hours, I'm at 84. And at 4 hours, I'm at 100. Okay, so here would be my graph. It is going to be a straight line, so it is a linear relationship. Okay, linear, but does not go through the origin. Okay, so that means that it is non-proportional. It's a non-proportional relationship. Okay, for problem 2 here, the next problem that we have, so we've got the weight in pounds. Again, this is our x. Our mass is going to be our y. So we want to know what is the constant rate of change. So what is the constant rate of change of this table? Eager? 9 over 20. So it does make it linear. Is it going to be proportional? Kingsley? Yes. Okay, eventually it will pass through the origin. So if we're taking a look here, for the change in our x, we're constantly increasing by 20. Increasing by 20 consistently. For our y, we're constantly increasing by 9. Okay, so we do have a constant rate of change that's going to be 9 over 20. That's as simplified as you're going to be able to get that. So 9 over 20, that is going to be our linear relationship. Okay, if we were to work backwards, then to go backwards, we would subtract 20, and that would bring us at 0. And then we would subtract 9, and that would bring us at 0. So we do happen to go to the origin. Okay, so when we're plotting our points, it is going to be plotted at the origin. Okay, I'm going to go ahead and count each of my weights in pounds by 10 because I'm going to have to get up to the 80 mark. So I'm going to go ahead and do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. I'm going to stop right here because I don't feel like graphing all of that. And then for my mass, which is my y values, I'm going to count those by 3s. So we have 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42. Okay, and if I'm graphing that, I graph at 0, 0. I'm going to graph at roughly right where we would have, right at the 20 and then the 9 mark. Then at 40, we're going to graph up at the 18 mark. At 60, we're over at the 27. And then at 80, we are at 36. Okay, so that does graph a nice straight line. It does have a constant rate of change. So it is linear. It goes to the origin. That means it's proportional. Okay, loaded into Google Classroom, you do have your assignment for today. It's some IXL skills. You've got 1 7th grade skill and 2 8th grade skills that are practicing what we've done here for linear relationships, graphing purposes, and proportionality.